Welcome to the lecture on synchronization within the kernel. So we will discuss all the mechanisms that are there that the Linux kernel uses for different kinds of synchronization primitives because the entire kernel is parallel. So all the threads that run in the kernel are running concurrently. So they will access a lot of data structures. And these data structures are basically parallel data structures, concurrent data structures. So we have two options. Either we can use old-fashioned locks, or we can go for lock-free programming where we don't have locks, but we have instructions such as atomic fetch and increment, compare and set, instructions of that type. So lock-free programming is of course much harder, and let's say writing a lock-free queue or a lock-free stack requires a fair amount of sophisticated expertise. So it is not that easy, right? The single enqueuer, single dequeuer is hard enough, but something more than that requires a fair amount of expertise, and that is not for most people. But kernel developers can do it. But that said and done, there are complexities involved. Furthermore, what can happen is that, there are a lot of things that can interrupt a process, including a kernel thread. For example, an interrupt can come, so the kernel thread will get swept out. Then the interrupt handler will run. Then the kernel thread will resume. So basically, the delay between consecutive instructions can be assumed to be very large and indefinite. Because the moment an interrupt comes, the interrupt handler runs, then the scheduler runs, and the scheduler can then go and run something else. All right. So if that happens, if something else comes in the middle, then of course there is a difficulty. So this difficulty has to be addressed. And that is why whatever algorithm you write, that algorithm has to assume that the delay between consecutive instructions is very large or can be very large. So the most basic type of lock that is there in the kernel is called a Spinlock. And this is similar to the locks that we have seen. So what happens is that one thread keeps on iterating over and over again on the lock variable until the lock is free. Once the lock is free, all the concurrent threads that want the lock try to atomically set it from free to busy. The one that is successful enters the critical section and begins to execute, and then you have an unlock. So it is as simple as that. So a Spinlock is something slightly more than that because it's in the kernel. So a Spinlock can be thought of that it is a lock on the CPU, it is not a lock on a resource, right? In a sense, of course, it is a lock on the resource, but it also locks the CPU in the sense that the thread cannot go off to sleep and preemption is not allowed. So let us say a thread has acquired a Spinlock. After that, preemption is not allowed in the sense that we cannot run some other thread. All right, so that is not allowed. Furthermore, Spinlocks can be used in the interrupt context because blocking is not permitted. So Spinlock basically means it's a very high priority lock. You take the lock, no other thread is allowed to run on the CPU. You finish the work and you release it. You are not allowed to make additional calls, go to the scheduler, run something else. That would violate the semantics of a Spinlock. A lot of this is enforced using disciplined programming, right? There is no hard and fast way of enforcing this. But the idea is like this, that when you acquire the Spinlock, preemption is turned off. Preemption is turned off basically means that no other thread can come and execute. And then you are supposed to finish the work and then release the Spinlock. So there is also a good reason why preemption is not allowed. So this can lead to a deadlock situation. Consider this fact that there is a thread that is having a Spinlock. Then let's say that there is preemption. Another thread will start running. If that tries to acquire the same Spinlock, it will not get it because the thread that has the lock is not executing. So it is not getting a chance to release it. That is why for such kind of locks, it's a good idea to turn off preemption such that whatever thread has the lock that gets a chance to finish the critical section and release the lock. So this is the logic behind turning off preemption. And as I have said, you also want to turn off migration, in the sense you don't want the thread to move to a different CPU and so on. So it's kind of a sensitive operation that you have the spin lock. You don't want anything else to run. You lock the CPU pretty much, and then you wait till the spin lock is released. Right? Even before doing things like bringing another thread or migrating a thread, you actually don't do that. So the key question is, in the case of a spin lock, how do you enable and disable preemption? In the sense, you have to tell the scheduler that do not preempt me. In the sense, do not stop this thread from executing and bring another thread in. So there has to be a very fast way of both enabling preemption and disabling preemption. So the kernel maintains a per CPU variable. We have already seen this in the sense of the current task pointer. So in the GS segment, the kernel maintains a per CPU variable that indicates whether preemption is allowed or not. All right. So if it is 0, it means preemption is allowed. If it is non-zero, it means preemption is not allowed. The way to enable and disable preemption is very interesting. So we have a little macro over here, which is defined in Linux preempt.h. It says hash define preempt disable. Preempt disable basically means disable preemption. All right. So what you do is that you call another macro preempt counting, which goes to the GS segment. So there is a variable there. So let's say the variable is v. It just increments the variable. So this means that preemption is disabled once. And then there is a barrier. The barrier is same as a memory barrier. It's like a fence. So that is there over here. So the do while 0 is a way of writing in the kernel to kind of tell the compiler that this is a block of code, right? So while 0 means that this is not going to iterate. And in this case, you can do a preempt counting many times, which means you can disable preemption, let's say 10 times. If you disable preemption 10 times, to get back preemption, you have to enable it 10 times, because enabling it does the reverse. So what it does is that you do a decrement and test. All right. So let me define preempt enable, which is the opposite macro of preempt disable. In the case of preempt enable, you first have a memory barrier to ensure that whatever you have done in your critical section, that is visible to the rest of the world, right? So that's the reason you have a fence. Otherwise, reordering will be there, that whatever is there in the critical section may actually be visible after this point, which is what you don't want. That is why always you encapsulate a critical section with memory fences. That part is done. Then what you do is that you decrement the variable, right? The variable that is stored in the GS segment, let's call it v, you decrement it. So then, as I said, if you disable preemption 10 times, you'll have to enable it 10 times, because it has to then come back to 0. So you decrement and test, right? So why do you have this? Because you can acquire one spin lock, then one more, then one more. So then the count will start with 0. This will be 1, this will be 2, this will be 3. And then you'll have an unlock, one more unlock, one more unlock. At the end of this will be 2, this will be 1, and this will be 0. All right. So in one case, you are disabling preemption. In the other case, you are enabling preemption. So the final count becomes 0. But because most of the time the value is non-zero, that is why you have this unlikely hint to the branch predictor. So now what happens is that you call underscore preempt schedule. What preempt schedule does is that, so when is this triggered? This is triggered when the count actually reaches 0. When the count reaches 0, it means that preemption is enabled now. So then what happens is that preempt schedule is called. So the scheduler function's schedule is called. So what that does is that then it looks for other tasks that wanted to run on this CPU. It finds them and it runs them. All right. So this is the entire story behind enabling preemption and disabling preemption in the context of a spin lock. And a spin lock as such is quite simple. So we'll see how it is done. But it is basically a classical busy wait loop. where you keep on checking the value, and if it is free, you acquire it, else you keep on checking. So let us now discuss the way that Spinlocks are implemented. So you will find an include Linux spinlock.h, and then of course there can be different variants depending upon the architecture. So in the case of an x86 architecture, the raw Spinlock class is used. So this is basically encapsulating an architectural Spinlock because you would require access to the atomic instructions that your architecture defines. Different architectures would define different atomic instructions, which is why we will have different architectural Spinlocks. That part is fine. So as I said, what can happen in this entire lock business is that you could have a deadlock. Deadlocks can be of different types. Deadlock can be that I am waiting for a lock, then this process is waiting for a lock, so on and so forth, and you have a cycle. That is one kind of a deadlock. The other kind of a deadlock is that the process that has acquired the lock is not getting a chance to execute. So you acquire the lock, but it turns out that the scheduler decides to run something else, and then you don't get a chance to execute, you don't release the lock, and the other threads that are trying to acquire the lock, they keep on busy waiting. So the CPU and the OS think that they are actually doing useful work, but they are not doing useful work. The only work that they are doing is continuing to ping the lock to find if it is free or not, right? So that does not count as useful work. So that is why you have a lock dependence map that tracks who has acquired what and who is waiting for what, so on and so forth. This helps you catch deadlocks, and it also allows you for deadlock avoidance, which basically means if you are trying to acquire a lock, then before you acquire the lock, the system will tell you whether it will lead to a deadlock or not. If it will lead to a deadlock, you may want to back off. So this is a debug time feature of the Linux kernel, which is not enabled in the actual release mode. But when you are debugging, the lock dependence map is very useful. So we'll study it. It's a very useful tool. So it's kind of like an assert statement. So all of you have seen assert, right? So assert is defined in assert.h, where you do an assert on a condition. So whenever you write C code, C++ code, you are supposed to have a lot of assert statements in your code to basically say that at this point of time, this condition should hold. At this point, this condition should hold, so on and so forth. Such that what happens is that if there is a bug, then the source of the bug and the point of detection are close, as opposed to detecting the bug much later when there is a segmentation fault. All right, so that is why. So this is something similar to that. It's a debug time feature. So the main idea here is to implement a lock and also some sort of a deadlock detector. So as you can see, this is a design pattern where a high-level lock, which is kind of a generic lock, is encapsulating a lock which is supposed to be specific to every architecture. And it is also including structures that are exclusively meant for debugging. So this is like a software architecture. It's a pattern, right? And it's a good pattern to follow because you would like to have a lot of things that are enabled at the time of debugging, which are not enabled at other times. So if I look at the inner workings of the Spinlock, this is the kernel core of a Spinlock. Don't get scared. We will look at it step by step. So first is that this is a classic ticket lock. So ticket lock is a classical paradigm for implementing a lock. So don't look at the code right now. Consider a bank. You go to a bank. So what is the first thing that you do? You go to a token machine and you press a button. All right. When you press a button, let's say a token with a number comes out. Let's say that number is 65. And currently the token that is being served is 55. So then you go and wait. You wait until the currently served token becomes 65. The moment your 65 and the 65 on the screen above, they match 65, 65, then actually you go to the teller in the bank and you get your job done, whatever it is that you want to do. So same thing happens in all queuing systems, banks, hospitals, everywhere, that we have this token system. So the same idea is implemented in the kernel where the token ID is nothing but the ticket ID because it's called a ticket lock. And a to be served is the one that needs to be served next. All right. So that is a to be served. Is exactly the same as what is there. So what you do is that both of these are 16-bit fields. They are nicely packed in an unsigned 32-bit integer. They are nicely packed in there, both of them, lower 16 bits, upper 16 bits. The 32 bits are nicely packed in a 32 unsigned 32-bit integer. All right. So what you do now is that the Spinlock T, the lock, in the case of x86 can be something very simple, that it can actually be an unsigned 32-bit integer. All right, as simple as that. So what you do is that you do an atomic fetch and add. So when you do an atomic fetch and add, what happens is that you fetch the previous value of the, so both of them combined is the lock, right? So you fetch the previous value of the lock. So the val over here is nothing but the previous value of the lock. And then you are adding one left shifted 16 positions, which will basically bring 1 here. So you are incrementing the ticket ID by 1. All right. So that is all that you are doing, is that you are incrementing the ticket ID by 1, which means if someone else comes after you, they get 1 more token, right? So that's exactly what happens with these coupons or tokens, that if you get 65, the person coming after you will get 66. That is precisely what is happening, that this ticket ID, once you get the existing ticket ID, it is getting incremented by 1. Because you are packing two 16-bit fields, right? And the upper 16 bits is a ticket ID, you are adding 1 left shifted 16 or 2 to the power 16, which is basically the LSB of the ticket ID. So adding it to 1 basically means incrementing the ticket ID, which is what you are doing. So then what is happening is that the old value of lock goes into the variable val. Furthermore, what you are doing next is that you are extracting the ticket out of val. Extracting the ticket out of val is as simple as right shifting this by 16 positions, which will provide you the ticket. Furthermore, the next is you need to find the to be served. All right. So to be served, let's call it TBS. If I typecast val to a 32-bit integer, then the lower 16 bits of val will actually become the value. All right. So if I typecast val, which is a 32-bit quantity, into an unsigned 16-bit quantity, what I will get is the to be served part. So if the ticket is equal to the to be served, then I am done. Right? So that basically means that, I just walk in, I take out a ticket, and the ticket matches the to be served. So I am done. I can just return. Done. Otherwise, what I need to do is that I need to busy wait. I need to wait. So far, so good. I need to wait. So this is where there is a complex macro whose job is to, it's a generic busy wait macro, which is used by a lot of other subsystems as well, which is why this is generalized. So the main idea is that on the memory address lock, you check for this condition. All right. So this condition may appear slightly weird because we have never seen a case in C where a condition is actually sent, and that too with a variable capital val which is not defined here. You don't see capital val being defined here. But as I said, a macro is different. A macro is given to the pre-compiler, pre-processor, not to the compiler. So the compiler essentially expands the macro and creates code out of it. So we will see the code that it creates. The basic idea here is that I'm sending a condition to the macro to busy wait and wait for it. Once it is done, I can do a barrier instruction because, as I said, every time you enter a lock, you need to have a fence. And the fence basically indicates that nothing after me can start before I have completed, and everything before me has to finish before I complete. So that's why a fence is always needed. But that said and done, we have the ticket ID and the to be served. All right. So let us look at this atomic conditional read acquire, which takes an address and a condition. right? So you take an address, the address is the pointer here and a conditional expression. That is all that you are doing. And you will keep on busy waiting on the pointer until your condition is true. Broadly speaking, that is the idea. So let us look at it step by step. So the first thing that you do is you essentially typecast this pointer to the type of whatever the pointer was. So what the precompiler will do is that if let's say this is int star, void star, whatever, right? In this case, unsigned int star, it will typecast pointer to underscore ptr such that the type is correct. That's all. Then what it will do is that it will define a variable capital var, which is basically the dereference type of pointer. All right. So basically, let's say that if the pointer is a pointer to a lock, then the capital val. So let's say if pointer is an int star, pointer to an integer, then val will be an integer. All right. That is the basic broad idea, that val is the value and pointer is the pointer to val. All right. So that is why this local variable is defined here. And then we have an infinite loop. So this thing that you are seeing over here is a way of creating an infinite loop out of a for statement. So we have already seen while one, that is a way of creating an infinite loop. In this case, we are creating an infinite loop out of a for loop. All right. So the for loop runs for an infinite number of times and until your condition is true. So this is the busy wait part. This is the Spinlock part. So what I do is I call another macro read once to read the value of the pointer. So then the value that I get is val. Then val is going as an input to my conditional expression over here, where I check if ticket is equal to u16 val. u16 val is to be served. So I'm just checking if the ticket is equal to be served. This is my conditional expression. So if conditional expression, it means that if this conditional expression is true, then I break. Otherwise, I keep repeating, but I take a little bit of a nap, in the sense I sleep for a random amount of time to minimize contention, right? To minimize contention on the same lock variable, I sleep for a little bit of time. Finally, what I do is the val is the value I need to return. I need to typecast and I need to return. So the standard way of returning from a macro is like this, where what I do is that star pointer, if it's an int star, star pointer is an int. So I just return the value that I read. And at this point of time, your condition is actually matching. All right. Okay. So then once the busy wait is complete, I do a memory barrier. MB stands for memory barrier. And a memory barrier is done and we are done. All right. So the lock is acquired. So this is the classical ticket lock, which is fashioned exactly the same way that we take tokens in a bank. And the queue management is done. So if I look at the unlock function, that is simple. So again, it takes an architectural Spinlock as the argument. So what you do is that in the case of an unlock, let us actually look at this backwards. So let us see the last statement. Then we will actually work our way backwards. It's much easier to understand it that way. So what I do is I do an SMP store release, which basically sets the value of a pointer to a value, and it also has a built-in memory fence, right? So it actually has both. So what I do is I take a pointer, which is a pointer to the lock variable, and I set it the value u16 val plus 1. All right. So u16 val is the to be served. So when I release something, or when let's say that the bank has finished servicing a request, what you do is you increment to be served. In this case, u32 val is the value that you are reading for the lock. So what you do is that you increment to be served, which is what I get if I typecast it to a 16-bit number. So this I incremented to 1, so my to be served is 1, and I put the value in the pointer. All right. And the pointer is where? So the pointer, if you see, the pointer should be actually pointing to here, which is the start of to be served. All right. So here there is little bit of a problem, because if I define a U16 star pointer, is actually a pointer to the lock, but here there is a question of little endian and big endian. So if you recall, little endian was a case where the least significant byte was stored at the lowest position, and big endian was the opposite. So that is why the pointer to the lock and pointer to be served may not be the same. It depends on whether the machine is little endian or big endian. That is why you use a macro. If it is big endian, you return 1. So basically you need to understand a thing with pointer math. If let's say I have an int star p and then I do p plus 1, I'm not adding 1. I'm actually adding the size of an integer, which is 4. All right. So this is a classical piece of pointer math, that whenever I'm adding or subtracting something from a pointer, I'm actually not adding or subtracting my argument. It's my argument multiplied with the size of the data that it is pointing to. So let us say it's a pointer to, let's say, doubles, which are 8 bytes, and I add 4. In reality, it is actually adding 32. So in this case, if I'm adding 1, it is actually adding the size of U16, which is 2 bytes. So this little endian, big endian thing is there. So little endian, no issue, but big endian, this correction has to be done, because Linux is meant to run on all kinds of machines. So once this basic correction is done and you get the pointer to be served, then you put the new value of to be served in the pointer and you are done. Right? As simple as that. This is the lock release part. And clearly you are seeing 2 words over here, acquire over here and release over here. So acquire and release can be thought of as kind of half fences, right? Kind of half memory barriers. For what an acquire says, that let's say you're doing a lock acquire. So acquire says, I don't care what happened before me, preceding. Everything in the critical section and beyond need to complete after the acquire is completed, which means the rest of the world should see that a lock was acquired, and then the critical sections changes happen. A release, on the other hand, says, I don't care what happened after me, I care what happened before me, which means everything before me should complete and then I should release. So when you are releasing a lock, you would use the release fence, basically because it would say that whatever has happened before me, that should be visible, then I should be visible. All right. So the acquire and release, all the theorems that we have seen will hold if we replace a full fence with a half fence. Where when you acquire a lock, you use the acquire fence, and when you release a lock, you use the release fence, right? So the half fence is a good idea because it is more performance efficient, easier to implement also. Let us now look at the next part, which is a trylock. So a trylock is like kind of a fast forward thing, where let's say that you go into a bank and you see nobody is there. Then maybe it's not a bad idea to directly try to go to the counter and get yourself served. So what you do is that you take the lock and you do an atomic read. So the entire contents come to old. Then what you do is that you right shift old by 16 positions. The moment you do that, this becomes the value of ticket. And you compute an AND with 0x FFFF 4Fs. Essentially, that is 16 bits. So when you compute an AND with that, this becomes to be served. All right. If both of them are equal, then you may be done, right? In a sense, you'll have to update the state, but if both of them are not equal, it means that there are other threads in the queue, so you just return false and you bail out if they are not equal. If ticket and to be served are not equal, it means your time has not come. If your time has come, you use an atomic compare and exchange, which for the lock variable, if the value of lock is still equal to old, which is what you read here, if it's still equal to old, you replace it with old plus 1 left shifted 16, which means you increment the ticket and you replace it with that, and this part is done atomically. This ensures that in one go you can do. If you are successful, you return true. If you are not successful, you return false. If you return false, what it means is that this is you need to fall back to the slower path, which is the regular lock, right, which was much slower. This is of course a faster one. So that is why what is done in Linux is you first try to acquire the lock using the fast path. If the fast path is not successful, then you try to acquire the lock using the slow path. So Spinlocks and interrupts are kind of interesting if you look at their interaction. Now that we have seen what a Spinlock is. So interrupts can still be processed. Even if the CPU is waiting on a Spinlock, right? Let's say you're busy waiting, interrupts can still be processed. Why not? Why do you want to delay an interrupt? But the issue is that an interrupt handler, let's say that you are holding a Spinlock. The interrupt handler may try to acquire the same Spinlock. That would lead to a deadlock because the interrupt handler has a much higher priority. So that is why you should use safer variants of the function. There are safer variants called the IRQ variants of the function. What they do is that in the critical section, they enable interrupts. And then when you release, you disable, in the critical section, you disable interrupts. And when you release, you enable. Because then this kind of a deadlock will not happen, right? So if I use, instead of raw Spinlock, I do raw Spinlock IRQ and raw spin unlock IRQ. So what happens is this ensures that you will not have this interrupt kind of deadlock, where the interrupt handler is running, that is trying to acquire, but again, the Spinlock is held by someone else. So what happens is that there is a little bit of a complexity here also, right? Every point in the kernel, if one door is open, two windows are open, but if you fall down the window, you'll break your leg, right? It's pretty much like that. So what you do is that consider raw spin unlock IRQ. You don't want to enable all interrupts, right? Maybe some interrupts were disabled to begin with, right? You don't want to go and enable them. That is why you use an IRQ save and restore version, where when you disable, it actually stores all the IRQs that were disabled to begin with. Then when you enable, you only enable those interrupts that you had disabled, not the ones that were disabled prior to that. So there are safer versions of this. So everybody is expected to use IRQ save and IRQ restore. Of course, they have a higher latency, so it depends. In general, IRQ save and IRQ restore are good. But sometimes when you're absolutely sure that nothing wrong will happen, or let's say that there are no interrupts involved in this case, then it's not a bad idea to use the unsafe versions. So your lock dependence map structure precisely tracks such kind of accesses. So now that we have seen Spinlocks, we should go to a kernel mutex. So mutex is kind of like a process lock, what we saw in the case of pthreads. So a Spinlock is actually like a lock overloaded, right? That it is disabling preemption, then enabling preemption. So a Spinlock is pretty much a lock that is held by a CPU. But a mutex, kernel mutex is held by a task. And in this case, task can go off to sleep and so on. So it does not have the additional riders that Spinlocks have. So a mutex is built on the foundation that Spinlocks provide. So you have an owner, which is a pointer to a task struct star. And it was actually meant, it's kind of a generic thing, anybody can be the owner. In this case, it's a task struct star. Then what it has is that it has a waiting list of contending processes, which are basically processes that are desirable of being an owner, but are not the owners. And this linked list, that is protected by a Spinlock, such that you don't have concurrent accesses. And the Spinlock that is protecting this linked list is waitlock. All right. So as you can see, it is nicely. So in this case, mutex is not using that arc Spinlock. It is using the wrapper on top of that, because this part of the kernel code, you want it to be generic. And then, of course, again, we have a lock dependence map which checks for deadlocks. So mutex locking is actually quite simple. So what you do is that if you are calling this in an atomic context, or basically in an interrupt context. So it is not allowed, right? You cannot call a kernel mutex in an interrupt context. So in this case, what you do is that because sleeping is not allowed, if it is called in an atomic context, you print the entire stack trace, you find out how you reach this point, because this is essentially an undesirable path. Assume it's not the case. You first do a fast lock. At least you attempt to get the lock. If you don't get it by the fast path, then you try to get it via the slow path. Okay, so you always have a fast path, slow path kind of thing. So the fast path in this case is in compare and exchange, the one that we have seen earlier. The slow path, on the other hand, is slightly different. Okay, the slow path, on the other hand, is you may, in case you cannot acquire it, you make the process sleep and you put it in an uninterruptible state. So you essentially put the process sleep, it is not interruptible, and we'll find a different way of waking it up. So an uninterruptible process can always be woken up. That is not an issue. It is just that it cannot process signals. But in any case, it's a kernel thread, and anyway, signals are not sent to them. So you put it in an uninterruptible sleep. It's good for the scheduler also, because it knows that the only thing good that is going to happen here is that this is going to get woken up, and that's all. All right, so far so good. And so you do the fast path, slow path thing. So the fast path, slow path here is slightly different. It is not the case. So it doesn't really work the way the ticket lock worked with a ticket ID and to be served. It is slightly different. So let's see what happens. The fast path in this case is that you do a compare and exchange on the owner field, right? So what you have is that you have the owner field over here. And you have some more information to indicate if the lock is free or busy. So let's say if this is the owner field and the lock is free. Then you try to do an atomic compare and exchange where you try to replace this with a new owner and busy, both together. So this is the advantage of packing multiple fields in actually the same 32-bit or 64-bit memory word and doing an atomic operation on them. So in this case, the idea basically is that you try to atomically switch both the pieces of information, free owner with busy and new owner. All right. If it works well and good, you are done. This is the fast part. If it does not work, right, then you are in trouble. You have to go to the slow path. So you acquire the Spinlock on the list of waiting processes. This is happening in the kernel, all right. Then the current task is added to the waiting list. Then the state, as we have discussed, is set to uninterruptible. But it could be interruptible in some cases, but assume it is uninterruptible. And then once the current state has gone into waiting, the scheduler can be called to run something else. All right, so far so good. So here a different kind of fast path is an operation. So that's all right. So when you will just going back to this, so then whenever a thread wakes up, whenever one of the, let's say the owner exits, the owner will check the waiting queue and wake up one thread if it exists. All right. So it's a simple idea that when you are trying to enter, you try to force your way in. If you cannot force your way in, you get added to the waiting list. And when the owner is leaving, the owner checks the waiting list and tries to wake up a process. All right. So removes it, makes it the new owner and tries to wake it up. So there are many kinds of locks within the kernel. So basically, this is an expanding list. And Spinlock is one kind. The mutex is one kind that uses the Spinlock. Then you have a queued Spinlock or an MCS lock, which is actually quite efficient in practice. So in this case, what you do is you create a linked list of nodes similar to what was done in a mutex. And the current node, which is basically the current process, is added to the end of the list. It uses extensive lock-free programming to manage the list. All right, so the list is managed. The list does not have a Spinlock to protect it. The list is a lock-free list. It's reasonably scalable. A great advantage of it is that it is very cache efficient. So interaction with the cache and the memory system is something that you have to consider when you are writing low-level code, right? It's very important. So it eliminates cache line bouncing, right? So it is done in such a way that it's not the case that one data item is there in the cache of one core, then after some point of time another core. That does not happen. So how does it not happen? Because all the reads and writes are on a local copy of the variable, right? And when any other core needs it, then the entire contents of the cache line are transferred to it, so you don't have fault sharing. But most of the action happens on a local copy, not on a remote copy. Then we have the OSQ lock, a variant of MCS, and the kernel also defines its own reader-writer lock known as QRW lock. And the code of this can be seen, right? But the basic idea is the same. Everything is there in /kernel/locking. So /kernel is the main directory for this like core kernel functionality. Is locking directory has everything of this type. So next we will discuss semaphores within the kernel. So we'll now look at semaphores in the kernel. So semaphores in the kernel are more or less the same as semaphores that are used in user space. So here the broad idea is that we have a count, and the count is the central concept in a semaphore. And then we have a waiting list of processes and a Spinlock. The role of the Spinlock is to protect the shared variable. So whenever you have a shared variable, you need a lock, because otherwise you'll have concurrent accesses, you'll have a data race. A lock is always required. Similar to wait and post, here you have up and down. All right. So down would mean that you would sort of keep on posting until you go down to 0. And so basically, sorry, I stand corrected. So whenever you are acquiring the semaphore, right, you would keep on acquiring it. But let's say if you want to acquire, but you cannot acquire, right? So down is basically the same as wait. So, and let's say if the count is already at 0. If the count is already at 0, then you set the current state typically to uninterruptible, because it is in the kernel and you don't want it to process signals and so on. Signals is a user space thing. So if it is at 0, you can't kind of down it anymore. It's not going to become negative. So that is why you wait and you make it uninterruptible. And up is the same as post. So what you do is you just do an up, up, up. All right. And so then what happens is that you take any waiting thread, you set its state to running, and you call the scheduler. So whenever you change the state of any thread, let us say that it's a general thing that you are converting it to interruptible, uninterruptible, or you are converting it to running. Running means you're waking it up. So when you say you want to wake up a thread in the kernel, what you do is you change its state. The moment you change its state, it is ready to run, but it's not running yet, or it's not even being considered to be run unless you call the schedule function of the scheduler. So any such state change, there is a need to actually go to the scheduler. So now we will discuss the lockdep or the lock dependence mechanism, which is like a lock avoidance mechanism. So lock avoidance means that before you acquire a lock, you check if this lock is acquired, can it lead to a deadlock? May not be an immediate deadlock, there could be a deadlock in the future. The question is it leading us to a risky situation or not? Which is why you need to be conservative. You need to avoid situations that may lead to a deadlock. That is why there is a need to be quite conservative. And you need a lock validator, which, let's say in the debug mode, will print that something risky is happening. So then the programmer will be aware, and then the kernel can be changed to avoid this risky situation. So we are aware of one kind of deadlock, which is a simple kind, which is where you have a simple circular wait. So of course we can have a trivial deadlock where I have one lock waiting for the other, and this is a trivial deadlock. Think of this as a non-trivial deadlock. But basically you have a circular wait kind of situation. And the circular wait is again a problematic thing. But this is unfortunately not the only kind of deadlock. There is another deadlock which arises out of what is called context inconsistency. So this sounds to be a hi-fi term. It is not. So the idea here is quite simple, that whenever a lock is acquired, all right, the lock acquire function in lock dependence is called. The job of this function is to actually check if acquiring the lock will lead or will possibly lead to a problem or not. So it first does a few trivial checks. The first is that, let's say I want to acquire 11 locks, but I have space, my resources are only for, let's say, 10 locks. Beyond that, maybe I'll run out of memory or something will happen. Then maybe I will not be able to acquire the 11th lock. My process can stall for some other reason. But if I don't acquire it, I'll not be able to release all the locks. So it's a good idea to limit the number of locks that a process can have at the same time. This is known as the lock depth. So lock depth is the number of locks that the current task can acquire at one point. That's like the maximum number. And the reason for this is quite straightforward. The reason is that the number cannot be exceeded, because then there may be other kinds of issues for which the task will get stalled. The moment it is stalled, it can't release any of the locks that it has acquired. The other is that, let's say if there has been a chain of lock, acquire, unlock, acquire, release operations, you want to, and now you are proposing to acquire a lock. The entire chain, let's say from some point, has to be validated. Does it look like a safe chain or is it an unsafe chain, right? Does it look safe or does it look unsafe? So you would want to validate your Spinlocks, your mutexes, reader-writer locks. You would like to validate everything and sort of certify that acquiring this lock appears to be safe, so you can go ahead and acquire it. So if we look at validate chain for, let's say, Spinlock kind of situations, or any kind of situation, so let's generalize it, you can define 4 kinds of states. So this is the state of what? It is a state of a lock acquire, or an instance where you acquire the lock, right? It's the state of a lock acquisition. So you can have 4 kinds of states. So soft IRQ safe, soft IRQ unsafe, hard IRQ safe, hard IRQ unsafe. So soft IRQ safe lock. So the lock is not soft IRQ safe. The acquisition is soft IRQ safe, right? So it's just an instance of lock acquisition. So that's why the word instance has been kept here. It means that when soft IRQs are disabled, so there are functions in the kernel that disable soft IRQs. So soft IRQ safe means that in an environment where soft IRQs were disabled, this lock was acquired. Hence, this lock acquisition is hereby tagged soft IRQ safe. That is all that you are recording. That when the lock was acquired, this was the prevailing environment. Similarly, you can have a soft IRQ unsafe where the lock was acquired when soft IRQs were enabled, which means that sometime in the past, well, not sometime in the past, you had enabled soft IRQs, right? And at the moment I am acquiring a lock where soft IRQs are enabled, hence my lock acquisition is soft IRQ unsafe. All right. So on similar lines, you can define hard IRQ safe, right? If all interrupts are disabled, it is hard IRQ unsafe. If interrupts are enabled, it is hard IRQ unsafe. So it is easy to see that if it is soft IRQ unsafe, which means soft IRQs are enabled, then hard IRQs are also enabled because hard IRQs have a higher priority. So if something is soft IRQ unsafe, it is also hard IRQ unsafe. Not the converse doesn't hold. So first is you look for trivial deadlocks. You should not have an A waiting for B, B waiting for A kind of situation. Another thing that the Linux kernel kind of enforces, and again, as I said, these are conservative rules to ensure that there is no deadlock for sure. When you follow these rules, perhaps things will get slightly more inflexible for you. You pay that price, but at least I am guaranteeing that lock dependence is guaranteeing there will be no deadlocks. In any chain, if you see A to B, I mean lock A and then lock B, and maybe you release something and did whatever, but then B and A, this sounds to be risky. This means that there are processes in the system that are not observing the A to B rule. So some process is acquiring, A first and then B. Some other process is acquiring B first and then A. That should never be there in a chain. So this may not be a deadlock situation now, but who knows? The code is written in such a way there could be a deadlock later. See, whenever you debug, you are debugging it for the real world, right? So you are debugging it on your console, but then you are debugging it for the real world, where you will run it in the real world, and then you don't want any problem there. So it's better to be safe in the lab. That is why you would not want this lock inversions to happen. The other is that you don't want a lock path, right? Chain of lock acquisitions to have both hard IRQ unsafe and hard IRQ safe, or soft IRQ unsafe and soft IRQ safe. Why is this? This is the problem of context inconsistency. All right. As I said, the name sounds quite involved. It is actually not that involved once I explain to you what this is. So let me explain what this is in reasonably simple terms. So what this is that, let us say you acquire a lock in a soft IRQ unsafe state, which means soft IRQs are allowed. So let us say you lock A. And then after some time, because soft IRQs are enabled, the soft IRQ starts running. That has a higher priority than the process context. It again attempts a lock. There will be a problem. The problem is A is already locked by a lower priority process, which is in, or a lower priority kernel thread, which is in process context. Now you are in a soft IRQ, means you will perennially have higher priority. You'll never allow that process to run. Yet you covet the same lock. That is not possible, because you will keep spinning, nothing will happen, and the kernel thread that has the lock will never get a chance to run because you have a higher priority. We have a deadlock. There is no circular way, but because the thread that owns the lock is not being given a chance to run, it will never release the lock. So this is a context inconsistency, because a lock which was supposed to be used in a soft IRQ safe state is now being used in a soft IRQ unsafe state. So what lock dependence says is that if a lock class is always in soft IRQ safe state, let it be like that. Then at least another soft IRQ will not displace it. If it's always unsafe, it means that you have some additional logic in your program to ensure that such kind of issues don't happen. But the moment you do a safe and an unsafe, it is suggestive of the fact that you have not applied any thinking. That is why these context inconsistencies are flagged, because it was seen that most of the context related deadlocks were happening because of this reason, that people did not give themselves the discipline of when to use what lock, and everything cannot be enforced programmatically. Right? The programming language is not that inflexible or not that rigid that it will stop all such behaviors. So some such checks enforce programmer discipline, which is why I made a point that creating methods to debug your program or enforce parts of it are right by construction is the best way to write bug-free code. Now, the Linux kernel has several more tricks up its sleeve. Now you consider, let's say, circular kind of deadlocks. A acquires B, B, C. So then what? You basically have, you have a chain, you create a graph out of it, right? And then in the graph, you search for cycles. Searching for cycles, if you use breadth first search or depth first search, requires, let's say, order V plus E cycles. If order E is roughly quadratic, it's roughly quadratic. This is quite slow. So it so happens, so this is where you use patterns. You don't want to use these quadratic time algorithms for every lock acquisition. So this is where there's a brilliant idea that you use patterns. It was found or has been found or has been observed that most of the time in kernel code, this chain of lock acquisitions are kind of these common patterns tend to repeat. So what you do is that you take a chain and you take a chain over here, and then you create a hash of this entire chain like a blockchain, right? So an entire chain of acquisitions, you kind of hash it like a blockchain. And then for the hash, you store a status. Was it found to be safe or not in the past? Which means anytime you find a new chain or a new, you create a hash of it, and at that point you do cycle detection, but you don't do it later. You're doing cycle detection, checking for context inconsistency, everything. You just write in this hash table, is it safe or not? Is it okay or not? If it is not okay, there is a problem. If it's okay, there is no issue. So then what happens is that using this fast technique, you don't have to do cycle detection all the time. That is not required. All right. So cycle detection is definitely not required all the time. And instead, what you can do is you can use this quick hash-based technique, hash table-based technique, to certify whether a chain of lock acquisitions looks all right or not. And this is reliant on the fact that such sort of patterns normally exist in the kernel. So now we are kind of done with the kernel synchronization part. So we will look at the RCU mechanism, which is arguably perhaps the most important export from the Linux world to the rest of the world in terms of synchronization. It's a new kind of paradigm of synchronization, which is extremely efficient. So in the next lecture, we will discuss the RCU, the read, copy, update mechanism.